Now let us try to understand about port delays. So these are the following topics that we are going to discuss. That is port delay. Next one is input availability. Next is minimum and maximum availability time. That is minimum time called as earliest time, maximum time called as latest time. And next concept is multiple clocks. And after that we shall see about understanding input arrival time. Let us see port delays. Once the clock constraints are applied, all register to register paths can be timed. So we have seen so many clock constraints like create clock, create generated clock, set clock latency, set clock transition, and so on. Next, delay constraints must be applied on non-clock ports, that is input ports and output ports. Earlier, the clock constraints that we have applied will work for register to register parts. Now we have to apply for non-clock ports, which are nothing but input and output port. As we know, there will be 4 timing parts, that is input to register, register to register, register to output, and input to output. If these input and output port constraints are not specified, timing analysis tools make an overly optimistic assumption about the interface timing. They assume that the combinational logic inside the block can utilize the entire clock period, leaving no time margin for the portion of the signal outside the block. Let's see about input availability. For each input port, we must specify the time at which the input signal becomes available. So if you see this particular figure, we need to specify the amount of time it takes for the data to be available at this particular port, that is I1. Consider the figure shown. So this is a figure. For block B1, we need to know when the signal arrives at input 1. So as I told, we need to know when the signal arrives at this input I1. This information helps the implementation tools. So here the implementation tools are nothing but you can take Cadence Innovus for PNR, determines how much time is available for the combinational logic C1 between the input port and the first register. So if we get to know the amount of time that it takes for the data to be available at I1, so depending upon that, some delay will get added according to the C1. Here C1 is nothing but combinational block, so it will have some combo delay. So the delay of this I1 followed by this C1 is nothing but the total time it is taking for the data to be available at the data pin of the flip-flop F1. It also defines the level of optimization required and allows STA tools to check whether the signal reaches register F1 in time to be latched correctly after passing through C1. So first we have to get to know like how much time it is taking for the data to be available at I1, followed by this data C1 gets added up. Then we'll get to know the final time that is taking to be available at this particular data pin F1. Now consider this figure 9.2 for block B2. So here this is the block B2, this is the block B1. If you see this particular figure, we are getting the data at I1 from the block B1. This is something which is present outside. So this is something which is present outside. For its input I1, we need to specify the input arrival time. The signal originates from flop F1 of the previous block B1. When its clock triggers, this clock edge serves as a reference event. Now here, this is a block B1. So the data that should arrive at this particular input I1 depends upon the clock C1. Why? Because whenever this clock 1 triggers, then only data comes from D to Q. So that Q data which is present at the Q pin will have some amount of combo delay of C1 followed by C2 and some wire delay, so that will be the final time for the data to be available at input I1. So here according to the figure, so here the block B1, so here the reference event is with respect to clock 1. So see here, after this reference event, the signal passes through clock to Q delay of flip-flop 1. So whenever here clock triggers, then only data will be available from D to Q. So it will have some amount of delay called as clock to Q delay, followed by the combinational logic delay of C1, which is from block B1, followed by this combinational logic C2. Here you can consider, suppose this is one block, this is another block, and this is overall present in one top level hierarchy. So that's why we need to consider this C2 as some top level block, and then interconnect delay through the wires, followed by these interconnect delays will be present, so that after that all these delays only we will get to know like how much time it is taking for the data to be available at this input I1. So however, for the purpose of defining input arrival time at I1, it does not matter how this total delay is distributed among these elements. What matters is how long after the reference event the signal reaches the input port. A late arriving signal at the input means there will be less time available for the logic cloud C3, the portion between the input port and the next register. So in order to understand this point, we need to see one of the example. In the upcoming slides, I will show you that. Now let us see what are minimum and maximum availability time. It is not always possible to specify the exact time when a signal becomes available at the input port. So we cannot say the exact time at which the data will be present at this input port I1. There may be multiple parts from the same reference event or PVT variations. Here PVT is nothing but process voltage and temperature variations that introduce uncertainty in the signal's arrival time. So if you see this particular figure, we want data at this input I1, but this data will be arriving from this flop followed by combo delay C1, and then C2 will get added so that the data will be available at I1. So this is one path. And another thing is from this flop, so it will have a delay of C1 complement followed by C2, and then data will be available. So in order to get this particular data, we are having two different parts. One is from this one C1 C2, another is from this flop C1 prime, C1 complement or else C2. So this is one other part. So it is having two parts. So that's why it is called as multi-path from same reference point. Why same reference point means here these two flops are getting triggered by means of one clock. So that's why it is called as multi-parts from same reference event. To handle this uncertainty, the designers must specify two timing limits. So first one, let us see about minimum arrival time. So which is nothing but the earliest arrival time. So it represents the earliest time at which the signal can change at the input port. Before this time, the input signal will not arrive and the previous value will be held stable. Suppose if we are latching one data, the data should get latched properly. So without getting this data latched, if previous data gets launched, then it leads to metastability. This minimum time helps ensure that the input signal does not violate the hold requirement of the receiving flip-flop F2. So here we are checking the hold condition. So here you need to know, like generally we know the setup and hold. Like for setup, generally required time should be greater than the arrival time, whereas for hold, arrival time should be greater than the required time. So let us see it by means of some of the examples in the upcoming slides. Now let us see maximum arrival time, which is also called as latest arrival time. So it represents the latest time by which the input signal will surely be available. So this is the final time by which the data should be available. This ensures that all signal transitions reach the input port within this time window. The maximum time is used to verify that the signal meets the setup requirement of the flip-flop inside block B2. So you can remember like this: for max delay it will be for setup, and for min delay it will be for hold. So similarly you can say like maximum arrival time will be calculating setup, and for minimum arrival time will be calculating hold. So see this figure. Figure 9.4 illustrates how the minimum and maximum arrival times define the data availability window for the input signal. So here this is the minimum delay and this is the maximum delay. So here the previous data is valid till this point, till this minimum delay, whereas after this max delay new data will be valid from here. Now let us see about multiple clocks. Sometimes an input signal may be triggered by multiple clocks. In the previous example we have seen there is only one reference event. You can see here the data is getting triggered by only one clock, whereas here the data is getting triggered by two different clocks, that is clock 1 and clock 2. So whenever clock 1 triggers, there will be some clock to Q delay followed by B1 delay and this combo delay, and data will be available. And one more path is whenever this clock 2 triggers, data will be available at Q pin. So it will be having some clock to Q delay followed by B2 and this combo delay, and data will be available at I1. So that's why I'm written this point. Sometimes an input signal may be triggered by multiple clocks. Consider the circuit shown in figure 9.5. So it is multiple reference events. The signal arriving at I1 could originate from clock 1 in block B1 or clock 2 in block B2. So it can be from this block or else it can be from this block. These clock events may be independent of each other. Why? Because here we are using two different clocks. So it is having two different clock domains. So they are not synchronous. Maybe we can say like clock 1 is slow or else clock 2 is slow. This is one condition. If not, this is slow, this is fast, or else clock 1 is fast, this is slow, or else fast and fast. So these are the different styles in which we can take the clocks. It depends upon the frequency and our requirement. In such cases, the input arrival time must be specified with respect to reference clock event. So it should be specified with respect to each and every clock. It is responsibility of the implementation tool and STA tools to consider all specified arrival times independently and ensure that both timing conditions are satisfied. So here the data can be available because of the triggering of clock 1, or else it can be from the clock 2. So that's why we need to define it properly while writing the constraint. So there will be a switch called as hyphen clock. So there you have to use a proper clock name, that is clock 1 if it is block 1 and clock 2 if it is block 2. Now let us understand about input arrival time. So consider the circuit in figure 9.1. So this is the figure. Suppose the earliest arrival time of the signal at input I1 is 3 nanosecond. Means the data will be available at this particular input I1 after 3 nanoseconds. So at 3 nanoseconds the data will be available, and the minimum delay of the combination logic C1 is 4 nanoseconds. So it is adding another delay of 4 nanoseconds. So for the data to be present from this outside portion of the design to this point is 3 nanoseconds, whereas this is contributing 4 nanoseconds of delay. So total 3 plus 4 will be 7 nanoseconds. So after 7 nanoseconds data will be available at this D pin. So that's what I mentioned it here. The earliest time the signal can reach flop 1 is 3 plus 4, which is 7 nanoseconds. So we are getting data at this data pin after 7 nanoseconds. Now here we are checking hold condition. So in hold condition we need to remember this formula, which is arrival time should be greater than the required time. So here this is called as an arrival time, whereas required time is calculated with respect to the clock. So required time is something which is time period minus setup. If we are calculating for setup, suppose if it is for hold, just we have to take only the hold time. Remember these 2 points. This is the arrival time which will be common. So arrival time will be 7 nanoseconds only. But as we are calculating hold, so this is the thing. 7 nanoseconds, which is nothing but arrival time, should be greater than the required time. So here required time is only hold time. As long as the hold requirement of F1 is less than 7 nanoseconds, the new value does not interfere with capturing the previous data. So this condition should be satisfied so that we won't get any hold violation. So 7 nanoseconds should be greater than the hold time, meaning hold time should be less than 7 nanoseconds. Then only we won't get any hold violation. Now consider the latest arrival time. Suppose the latest signal arriving at I1 is 5 nanoseconds. So here data will be available after 5 nanoseconds, and the maximum delay of C1 is 6 nanoseconds. So this is contributing 6 nanoseconds of delay. So total 6 plus 5 is 11 nanoseconds. After 11 nanoseconds, data is getting available at this particular data pin of flip-flop F1. So the latest time the signal can reach F1 is 5 plus 6, which is 11 nanoseconds. So here we are calculating setup. So for setup, we know the formula, that is required time should be greater than the arrival time. So required time is something which is calculated as total time period minus setup time of this particular flip-flop. Whereas if it is hold, it will be only the hold time. Remember this point. So here required time is total time period minus setup time should be greater than the arrival time. So arrival time is nothing but I1 plus C1. So I1 is 5 and this is 6. So 5 plus 6 is 11. So total time period minus setup should be greater than 11 nanoseconds. Then only we won't get any setup violation. So suppose if you are taking a setup time of 0.5 nanoseconds, which I have mentioned it here. If the setup requirement of F1 is 0.5 nanoseconds, then as long as the clock reaches F1 at 11.59 nanoseconds or later, the current value can be captured reliably. So here if you are taking a setup time of 0.5, so obviously time period should be 12 nanoseconds. Then only 12 nanoseconds minus 0.5 will be 11.5. Then only this condition will get satisfied. So here it will be 11.5 nanosecond, which is greater than 11 nanosecond. Then only we won't get any setup violation. This example shows how input arrival times and combinational delays determine the time margins for setup and hold checks in the STA. So remember these 2 points. So for this particular figure, setup, which is nothing but required time should be greater than the arrival time. So required time is nothing but total time period minus setup, whereas arrival time is nothing but the delay which is contributing by I1 and C1. If it is hold, arrival time should be greater than the required time. So arrival time is something which is I1 plus C1, that is 7 nanosecond, and here required time will be only hold time. There won't be any contribution from clock period. So in this video we have understood about port delay, and that specifically we have focused on the input port delay. So in the upcoming videos I'll explain about output port delay also. Thank you.